आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Purvasha Banerjee and Shushanto Das.
एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़, की आवाज़।
In this episode of the podcast, we are immensely happy to receive a discussion from Dr. Smarajit Polley. He will now be introducing himself and will be sharing his academic journey.
Thank you. Myself, Smarajit Polley. I am a researcher in the Department of Biological Sciences here in Bose Institute. Actually, my work started in Bose Institute, but I ended up in IICB because our lab moved there. Then I spent a considerable amount of time in California working in two institutes, University of California, San Diego and Salk Institute. And then I came back to India and joined Bose Institute.
Dr. Polley now explains his area of research in brief.
So the theme of my research is mechanism of fundamental cellular processes at high resolution, meaning a cell works on different proteins. So we are interested in a few class of proteins and we try to look into their mechanism of action using different techniques at very high resolution, say atomic resolutions.
Dr. Smarajit Polley will now be elaborate on that.
So I'll to go to an example before I go into the research. Say for example, a cricket ground. Okay, so there is a bowler bowling, a batsman batting, there is a wicketkeeper and there are fielders. At a given scenario, most of the fielders are not doing anything, but wicketkeeper is always working, right? But a fielder gets turned on when the batsman hits a ball towards him. Our cells are also like that. So there are thousands of proteins, they work, but not very actively all the time. But there are some proteins, they work very actively all the time. Even if those proteins that are not working very actively all the time, they do work very sharply when there is a signal coming. This signal can be a pathogenic insult, this signal can be something else, but those proteins that were kind of resting, not actually resting, they are ready to act, they start working. So in my lab, we work on some of these proteins. There are many others. We don't look at everything. These are called protein kinases. What they do? These are enzymes. They add phosphate groups to other proteins. What does happen? The moment they add some phosphate group to other proteins, those proteins change their behavior and they start functioning something that they are not doing before. So you want to look at how these enzymes work, how they choose a particular protein in a pool of say 20 or 30,000 proteins inside the cell when the batsman hits the ball towards them. So that is a theme of our research in one particular area.
So it is a playground.
Exactly, yes. So these kinases, there are 500 of them in our cells. we only look at, say, 4 or 5 of them. But the theme is these are related to either our immune system or neurological development, meaning they're required to keep you healthy. So if these kinases that go bad or they don't function, your immune system fails. And that can lead to immunological disorders, that can lead to cancer. In the neuronal scenario, say for example, you have a brain injury or neuron injury. These kinases start acting and your neuron grows back and it repairs the damage. If you don't act upon on these kinases, or if these kinases fail to act, your damage becomes permanent or you cannot repair them. So we are trying to understand these kinases, how they actually perform this function, if you can modulate them, or if you can go into a situation where they are not acting, but you push them to act. So this is what we are trying to do.
Professor Polley now speaks on the way forward.
Yeah. So as I said, our research is themed upon understanding the mechanism. And I truly believe any research that is truly in the discovery mode, they will be useful someday. For example, I'll give you an example. There are many examples actually, but I'll just give you one example. Say ACE, angiotensin converting enzyme drugs, for example, or for example, statin, those are cholesterol inhibitors, right? When they were discovered as medicine or used as medicine in particular diseases, their function were known long before. And when those work started, those researchers didn't know that these molecules will be used in those diseases. So in our case, what happens is that since these molecules are very intricately related to many diseases, if we understand the molecule better, if we can give the mechanism of their action at high resolution, they are my colleagues in this institute or elsewhere, they will use that information and they can use this information to generate drugs. I don't personally design drugs, and to be very honest, very few drugs have been designed as a tailor-made drug that somebody tried to design them and they got successful. It's a long-term process. For example, the medicines that I'm talking about, it took about 30 years to develop them into a medicine. But there were multiple researchers whose fundamental work led to that drug to be used in the market or to the patient. So we work in that area where these informations can be transmitted to my colleagues who are actively involved in drug discovery research, either in this institute or beyond this institute.
Professor Polley now speaks on his collaborators in India and abroad.
So we work very closely with some of my colleagues like Professor Kaushik Vishwas here. And beyond this institute, I have collaborators in the US. Also in this country, we work with scientists from Institute of Science, Cellular and Molecular Biology Institute in Hyderabad, National Brain Research Center in Gurgaon, and those kind of institutes.
Professor Smarajit Polley now shares the position of our country globally in this field.
So India has been very successful in this kind of research, this theme of research of understanding mechanism at high resolution for a very long time. So I'll just give you a historical perspective. The way we understand proteins these days, and there are some matrices that define whether the predicted structure or determined structures are right or wrong, that came from an Indian scientist called G.N. Ramachandran, long time back. So from his time, this kind of research has been going on where people are looking at the protein structures. Earlier, it was done by X-ray crystallography. Nowadays, it is done by cryo-electron microscopy mainly, but X-ray also works. So I would say India has a very good foundation of the structural biology work in this country. What I blend in, not just structure, but I introduce function and their relevance to the biological perspective. And India is doing extraordinarily well these days. And this community, this modern community is, I would say, they're at the forefront of this research. I cannot say they are the leaders. or they are at the very front, but they are among the front runners. So as I was telling that these kinases, for example, they are needed for your well-being, right? If they don't function, then your immunity is compromised, your brain development or some injury, you don't recover from them. So they are essential for your well-being. However, these kinases, if they overact or overreact, that could also be bad. Say if you take the example of the immune system, the kinases I'm talking about, they activate a particular transcription factor called nuclear factor kappa B or NF kappa B. Their action is very required. If you are attacked by a pathogen, you have to activate those transcription factors, and you have this kinase has to act, but up to a certain point. If they keep on acting, or if they just starts acting whenever there is no pathogen or something like that, they just get activated by themselves, that is bad. That leads to your autoimmune disorders or hyperimmunity, those kind of things. So these are molecules, they are friends in a situation and they are foes in a different situation. So they have to be active but not too active. So our job is to find out what makes them active, first one, and what makes them hyperactive. Or when they are hyperactive, how can you bring them back to their normal activity, right? So this is the cycle, or this is a whole, to get the whole picture, you have to understand how they are not active, how they are optimally active, how they are hyperactive, and how can you bring them back. So we work on the whole scenario, we try to work on the whole scenario and try to give a glimpse of the mechanism from where they are inactive, they are going to the active state, which is optimally active, they are going to the hyperactive state, and how they are coming back to their normal state. So this is how I, in a very loose or lucid term, I try to explain what we are trying to do.
We are extremely thankful to Professor Smarajit Polley for sharing his journey of exploring new areas of research with us. Thank you so much.